Cleaver, who has rushed down the railway lines from Sheffield Hallam University to get here just in time. Doug and I go back a long way, but enough said about that. And I'll simply hand over to him, and you can see his title there. So over to you, Doug.
Thanks. Yeah, so Mike said I came down on the train this morning, but to acclimatise myself into this workshop, I did have a look at on the website yesterday and tried identifying people from the backs of their heads on some of the videos. I looked at Mike's video. Part of what I do at Sheffield is try and train PhD students into how to give a talk, and one of the things you say to them is, be upbeat and don't start making excuses. So I've now got Mike's talk. Do look at it if you've not looked at it on the internet. Mike starts his talk saying, apologising for not being a mathematician, and saying he works in the theoretical physics department. Then he apologises for not actually being a theoretical physicist, or even not being a scientist. And then he makes this bold statement, don't worry, it can't get any worse than that. I was trained by Mike, so I'm one step even further divorced. I do computer simulations of various things. I'm going to talk about surfaces today because there's got some overlap with at least two lots of theoretical work, one of which I won't talk about because Paolo, who's in the front, I think is going to be talking about it, some density functional theory, which is distinctly linked to that. Actually, three pieces. It's not the Spanish Inquisition. A second piece of work I've done over the years with Nigel, which is related to this surface stuff. I've also been motivated at least by some things that I've done with Nigel. But what I'm going to talk about today is most recently benefited from input from Tim Atherton, who was originally in the UK but now is in Tufts University in Boston, and might be watching on the video if he's got up early. And it's also largely in collaboration with the University of Leeds physics department, Steve Evans, John Bramble is a PhD student, and good old Jim Henderson. When I was last in touch with Jim Henderson, he emailed me from his boat somewhere in Scotland. He does still exist, even though he's retired from Leeds. Scraping things off the bottoms of boats. This is main interface work at the moment. And this work was kind of born out of over a pizza in Constance between Jim and myself. Anyway, there are all kinds of uses of patterns to orient liquid crystals. You don't have to rub surfaces anymore. This goes back quite really a long way. So there's early ZBD papers from the Malvern group from back in 1997 using steric ridges in order to generate bistability. So a steric interaction, nothing to do with rubbing polymers or things like that. Another steric system came from Hewlett-Packard Labs sometime later. Then there's chemical stripe patterning, so the Clark group, Nick Abbott's done a lot of work on this kind of thing as well, and incorporating nanoparticles in as well, so the picture doesn't come up. You can change the geometry instead of having it 2D stripes, three-dimensional things and get a different symmetry of anchoring. Bistable things coming from square wells, the work, as I say, that Nigel and others have been involved with. Lots of clever routes for using patterning in order to mediate or control anchoring. The system that the Leeds group have been working on for various reasons, lots of biosensing and things like that type systems, is like this. It's closely related to the Nick Abbott approach. Essentially, you take your lump of gold and you dip it into a surfactant bath, and your surfactants have got a sulfur head group, which really likes the gold, so they want to sit on it and form a nice ordered monolayers, and that's the molecule, if you like. It's yellow, it must be sulfur, so that's strongly attracted to the gold surface. That's all you need to know. Except there's also a functionalized end group, so you can change the length of this thing and you can change the chemical nature of that end group, but that's going to be your energy parameter. These are some experimental results. These are measurements of the Brewster angle, refractive index. This is for our favourite liquid crystals, the NCBs. This is on one substrate. I think this is on an OH functionalised self-assembled monolayer. The second set is on a COOH functionalised monolayer. Essentially, these are all doing the same thing. You cool them down, and at the transition temperature, at 0, you get a jump in the refractive index. And that's because the liquid crystal is lining up planar on these substrates. If you change the head group, or change the functionalization, then you can get an opposite behavior. Instead of going down, the Brewster angle can go up. Okay, and so we cool it down, and you get a jump at the transition, the nematic isotropic transition temperature. And in this case, it's going up because the alignment is going homeotropic rather than going planar. So by changing the functionalization, the guys and leads can tune in either planar alignment or homeotropic alignment, depending on the chemical nature of the sound that they put on the gold. All well and good, that's nice. This one at the end looks like it's in a bit of a pickle. That's because it changes its mind. It thinks it wants to go homeotropic, but then you cool down a bit further and decides it wants to go planar. And they did a lot of work on this initially in the 1990s. Ban Al-Khairah was the relevant PhD student. She looked at lots of cyanobiphenyl, lots of functionalizations, and saw planar alignment on some, homeotropic alignment on others, and the occasional transition. And that's kind of where we came in. So Ban's work was looking at unpatterned substrates, but there was a mechanism for patterning with these things, which amounts to a microscopic version of potato printing. You get a polymer stamp which you create by pouring it into a mold which you've etched by electron microscopy. When I say you, I mean the experimental student in Leeds. And you can choose what pattern you like for that. You pour the plastic in, it forms this thing. Typical periodicity is tens of microns, fairly easily achievable. You ink your stamp with your surfactant material, and you just then plonk it down on the gold substrate, and where it touches, the SAMS sticks. Simple potato printing. And you end up with parts of your surface covered in SAM, bits which were in contact with the PDMS stamp, and they form nicely ordered monolayers where they touch. You then take your piece of gold and you stick it in a bucket containing another SAM, and it obediently backfills the bits that you haven't filled in previously. And that is a very reproducible and cheap way of achieving, let's say, micron scale patterning of whatever it is you decide to pattern on your initial PDMS stamp. And what we can do is use one functional end group for this self-assembled monolayer, another functional end group for the stuff that's in this bucket, so you can get competition between homeotropic aligning regions and planar aligning regions. You rinse it, you dry it, and then you pour a liquid crystal on top and you see what happens. These monolayers are extremely flat, so if you do an AFM scan on them, you can't see any features. But if you pour a liquid crystal on top, then you can see, because you get some of it being vertically aligned, some of it being horizontally aligned. So it's an amplifier, if you like, of this chemical pattern. Ooh. Don't worry, it's not a blank slide. There we go. Experimentally, this is what you do if you gently cool one of these systems down. It's in the isotropic phase at the moment, don't worry. This is a system which is patterned with squares of homeotropic and planar, random planar aligned regions. I think they're about 30 micron periodicity. So it's just starting to order up, and we can see, I think you can see at the back, there's some kind of definitely some square features going on there. So, well, surely that's the surface patterning coming through. I'm going to run it on, and it all disappears. Where's it gone? It's turned into, oh, that's just like a normal kind of Schlieren texture, isn't it? Where's the square patterning? Oh, did we do it right? What's happening? Ah, here it comes. Now this is really the square patterning. And I'll pause it again if I can. Lots of squares, certainly. We can see some dark bits and some light bits in domains. But if you look within the light areas, you can see there are some bright yellow bits and some brownish bits within there. So there's a kind of checkerboard pattern going on. And then a larger length scale, there are some domains forming. And the reason why we've got checkerboard is some of the squares, the direction is coming straight out. The top surface of this is uniform homeotropic. And others of the squares, it's planar, and the planar orientation is sitting at either plus 45 or minus 45 degrees, because there's spontaneous symmetry breaking. It could easily well be plus 45 or minus 45. And in the yellowish regions, the planar bits are at one of the 45s. In the dark regions, the dark domains, is at the other 45. And I'll prove that to you because if we play this on, then we're going to rotate the system by 45 degrees, and the dark domains are going to go light. And the light domains are going to go dark, okay? And that's because the planar regions are at either plus 45 or minus 45. And we've got two different flavors. So that in the yellow regions, the planar squares are at 145 degree. In the dark domains, the planar squares are at minus 45 degrees. That's why it goes light to darker. When you rotate the sample, this is through cross-polarization.
Sorry, where are the pure homeotropic?
The pure homeotropic ones are so the pale brown ones are the pure homeotropic. The bright yellow are the planar at 145 degree angle. The dark brown are the planar at the other 45 degree angle. If you look at it closely, the homeotropic squares in the dark region, the homeotropic squares in the light regions are pretty much the same colour. Okay, so you've got some pure homeotropic squares coming straight out.
Shouldn't they be the dark?
They're kind of tan brown, depends how they've done the optics. But the ones that are changing colour are the plus and minus 45 degree ones, definitely. Have to be.
So what have you printed on there?
So that's some squares with, I think, COOH in functionalisation, other squares with a CH3 in functionalisation.
Particularly regular pattern of homeotropic and planar.
Yeah, so it's a checkerboard, a chessboard arrangement of homeotropic aligning and planar aligning squares on a 30 micron periodicity.
Right. Yeah.
I suppose you can't rub these things. So what makes the parallel go at 45 and minus 45? The insane.
So here it's just random choice. Each pixel is deciding for itself, and that's why we've got domains of one or the other.
Yeah,
so
why does it not go in a different direction? There are only these two angles allowed.
Yeah, okay. I'll talk about why it goes to 45 degrees. Got a question, Nigel? Sure.
How thick is your liquid crystal layer?
This is several microns thick, and as I say, it's homeotropic at the top surface. I think it's free surface at the top, which is homeotropic, so they can see through it. So summarising, so you can see 4 distinct stages when you cool this liquid crystal on a monolayer. Black, isotropic. Then you see some presence of the patterning. That then goes away and becomes Schlieren-like. And it's only later that you get this this pattern that we've been talking about. Essentially, this is like domains. If you look in a 2D magnetic system, you get some up ones and some down ones. You've got some plus 45s and some minus 45s, but they're mixed in on a chessboard with some pure homeotropic square.
But by later you mean cooler? Or
Yes.
if you waited at a constant temperature,
No.
it's still cool?
It's cooler. It has to be cooler, yeah. Okay. I have slipped past you the evidence as to why this is happening. There is some experimental evidence as to why this is happening. I'll come back to that. I'm going to show you some simulation attempts at looking at this. Various questions. can we at least capture some of this behaviour using particle-based simulations and also with continuum theory? Everything I've shown you is obviously integrated across through the film, and there's not a good reliable way of getting the Z dependence experimentally. So it was a bit of a question, and also with some other patternings, there's some questions as to what's happening as a function of distance through the film.
What's the size of the squares, remind me?
Typically 30 microns.
30 microns.
30 micron edge length. What I'm interested in doing is looking for tilt and seeing if I can induce or control tilt using patterning. Independent control over the two anchoring coefficients, for example, would be a nice thing to explore. And there are all kinds of topologies of patterning one can dream up. So that was squares, because that was the video that John Bramwell presented to me. We've done lots of work on circles, on stripes, and we had to look at some other systems as well. So I'm going to show you some results for some really very simple particle-based simulations. We've done lots and lots of systems, all using a very simple model. This is an approximation to a hard ellipsoid fluid. It's a useful approximation because the contact function, the distance at which two particles are judged to collide with each other, is in an analytical form. That's kind of useful for a simulator. It becomes very useful if you're collaborating with a density functional theorist like Paolo, because it means that some of his integrals can be done analytically, and he saves various loops in his density functional theory. So there's an expression for the point at which, or the separation at which two particles are going to interact, are going to hit each other, and it's symmetric with respect to molecular axis vectors and things like that. And you compress an isotropic fluid and it becomes a pneumatic fluid. This model doesn't give you a synectic. It's slightly different it's formally different from the hard ellipsoid fluid, but qualitatively this thing does everything that the hard ellipsoid fluid does. And all my ellipsoids are going to be 3 times as long as they're wide. That forms a pneumatic. This is going to interact with the surface. We've tried lots of particle surface interactions over the years, and this one's very simple, but it does everything that the more sophisticated ones do as well. If we forget that our particles see each other as ellipsoids, and in terms of their interaction with the surface, let's just represent them as needles. So a needle with centre of mass the same as the centre of mass of the ellipsoidal particle, and it runs along the axis of the particle. If that needle is very short, if it's a point, then the particle can lose half of its volume out of the top of the surface. If the needle is very long, then it can't lose much of its volume out of the system by going vertically, but it can if it approaches horizontally. So what this particle surface interaction gives you is the ability to control anchoring using just the length of that molecular parameter, which is the length of the needle, which sits along the axis of the molecule. So as I say, if we try representing the thing, the ellipsoid in full, we get exactly the same qualitative behaviour. So as a function of this needle length, this is the behaviour we see when we gently compress a system. So we have loads and loads of systems. Most of them fairly small. We can make things bigger if we really need to. So if that needle length, Ks, if it's 0, it's just a point sitting at the centre of the particle, then I've got a wall at the top and a wall at the bottom, and the particles obediently sit homeotropic to that interface. If we make it a bit longer, length 1, where 3 is the length of the entire molecule, then it does very similar behaviour. Make it 1.5, then it still aligns homeotropically. Actually, when we look in detail at this 1.5 system, if we align it horizontally, it will stay horizontal. This is actually a bistable value for the needle length. But if we push it all the way up to 2 and compress, then we get random planar alignment. Make it even longer, then not surprisingly, again we get the system to line up flat against the walls. Kind of evidence that it's random planar. So here, colour coding represents orientations of the particles. So we've got blue axis is is homeotropic, and the yellow and green are the two planar axes. And we can measure various profiles across these systems to get out the structure. Again, this relates more to the density functional work than to the continuing theory I'm going to be mentioning in this work. We can look at the orientation order with respect to the surface normal. That's a very good indicator of what's going on. And here are a bunch of order parameters as a function of Z for these systems in their low density arrangements. So we get surface order, and if it's one of these systems, then the surface order parameter comes out towards 0.5 because they're being planar, and then we have an isotropic bulk. But if we're one of these guys at the top, then we get a positive surface order parameter. QZZ is large and positive in the surface regions. We see structure in there as well, which we can relate to the density profiles. And these all make quite a lot of sense. So here now are density profiles and order parameter QZZ profiles for the KS equals 0 system and for the KS equals 3 system. So the density profiles, as you can see, in the highest density arrangement, which is the pink line, we've got 6 reasonably ordered layers there. Things are still diffusing around fine here. Our density peaks aren't going to 0. If the troughs go to 0, that's an indication that things are locked in. We've clearly got interstitial particles. We get, not surprisingly, a higher frequency of density oscillation in the planar aligned system. We get many layers there, and to some extent, this is what you'd expect if you did simulation density functional theory of confined spheres. You get this kind of damped oscillatory behavior. But here, of course, we additionally have got the orientational behavior. So the highest density system here has got a high positive order parameter in the center. The highest density system here, the blue line, has got the most negative order parameter. So things are planar aligned in the center of the film. So let's try mixing these things together. How do we mix them together? Well, we allow this parameter, this surface interaction parameter, Ks, to vary in space. So here, I'm allowing it to vary smoothly, actually, as I go from the red region down to the green region. So green represents, that's when the molecules go on to lie planar. Ks is large. Red, there, and Ks is small. This is the point particle in the center, so they want to align up normal. We compress this system. So I've got continuous variation in this Ks parameter going across this arrangement, and that's what comes out. Locally, in the surface region, these particles are happy to select either homeotropic or planar. They never select a tilted orientation. I've got continuous variation of the Ks parameter here. It's like a fuzzy interface, if you like. But the system says, no, I've got to have a molecularly sharp interface between my two surface regions, between my homeotropically aligned and my planar aligned system. I've not put that in. Later on I will put that in, but it turns out it doesn't matter whether you allow it to choose it itself or if you impose a sharp interface between the two substrate regions, which is actually quite important experimentally. It perhaps explains why the patterns look so nice experimentally, because at the surface, things really do jump straight across.
But here, they're choosing that because the elasticity would be huge too.
Okay.
How many micro? There's
Yeah. So the reason why the green particles are pointing into the board is absolutely elasticity. Yeah.
What's the length of that box there?
Okay. So these are okay. So my simulations are 1,000 times smaller than the experiments. And that's part of the questions that we're going to come to later on. Which of these things can be shown at the molecular scale, which require continuum representation in order to understand the experiments? And it turns out there's some things that you can only see with simulation, something you can only see with experiment. You need the continuum theory to join the two together, which is good news. But we weren't really expecting to see things absolutely this sharp, these interfaces. Now, the experimental system I showed you, first of all, was, as I say, it was patterned on one surface and homeotropic on the bottom on the other. So this is the simulation equivalent to that experimental video that I showed you. So here we are, low density, let's say high temperature in the isotropic phase. You can see that I've got homeotropic alignment all the way along the bottom. At the top, I've got a random planar stripe, which you can even see some signs of in this. So the left-hand edge and the right-hand bit are going to end up being blue, and the middle bit's going to end up being green. But we've clearly got an isotropic arrangement here. We compressed it a little bit. We got aligned surface regions at the bottom. We got much more clearly aligned surface regions at the top. Still fairly isotropic in the center. Compress it a bit further, and the homeotropic has almost completely dominated this system. And yes, I know I've got homeotropic along the bottom. I've got a lot of homeotropic in my system. This happens time after time after time. Homeotropic is really, really dominant in almost all of these systems, at or even just below the TNI or rho NI. We compress that a bit further, you think, oh, homeotropic is going to win even more. But it doesn't. If you increase the nematic order, then the effect of this green region becomes greater. Okay, so at around transition, homeotropic wins. Only deeper into the nematic does the influence of this substrate pattern start to come through. And we see this again and again. And it's what we saw in the experiments. High temperature, you get surface alignment according to whatever the local surface wants to do. You cool that down, you get growth of the surface alignment, but you get different wetting in the homeotropic region from in the planar region. And this happens time and time again, experimentally and in the simulations. You get some continuous growth of the wetting layer, or of the wetting in the homeotropic regions, whereas you get hardly anything going on above TNI or below rho NI in the planar aligning regions. And this appears to be completely generic. I first started simulating liquid crystals using a lattice model, and in a lattice model, that asymmetry is just not present. Okay. Cool down even further, increase the density even further, and this continuous wetting of the homeotropic phase, if it's a small enough system, it becomes completely dominant. And this is what happened. And it's only later on that you get a discontinuous wetting from the planar region, and that then starts to bite later on. And that's why, in the video of the experimental system, you saw black, some surface features, Schlieren texture, full pattern. It's because of the different wetting behaviors of the homeotropic aligning and the planar aligning system. I said that there had been some evidence for this higher up in the talk, and it was in these ellipsometry results. In the planar aligning system, you cool it down, and at the transition, it jumps. You get a discontinuous change in the refractive index. In the homeotropic aligning system, look what happens above TNI. You don't get flat behavior, you get gradual growth. There's a thickening, a growing film above TNI in the homeotropic aligning system, and they see it for all of the NCBs on homeotropic aligning systems. So this rise here, which triggers, is a signal that you're getting different wetting behavior in the two subregions of the system. And it's because this one's winning at the transition, becomes dominant. It's only later on that the other guy, the influence of the other guy comes in. We see it time and time again. We've done lots of simulations and we've done lots of experiments, and it's very, very reproducible. It's not apparent from a continuum level or lattice model.
But but elastic behaviour, as Nigel pointed out, doesn't play a role in this at all.
No.
You could model it, for example, using a Swansig model, where there are just like 2 or 3 orientations of rods.
So the importance of elasticity is important at this point. But in terms of the high density structures that we get are determined by the balance between the surface terms and the bulk elastic terms. But the route by which it gets there is affected by the wetting behaviour.
Now can you go back to the one slide before that one? I lost it. I don't know where it is. The one that showed the snapshots on the right hand side, the sequence of 4 snapshots.
Yeah.
That one. Yeah, that one. So which of those snapshots are above row NI and which are below?
Okay, so this is the experimental data again. Whether 3 is from my simulation. In my simulations, I can't judge precisely. I can't judge where row NI is, particularly because I've got bits of particles escaping from out of my system, so I don't have a good definition of a row NI. The experimentalists, they put their 3 just above TNI. So I think so this is the temperature window of which that video is shot is really very narrow. So as soon as the data jumps down here, that's when we're into region 4. So it's large. So this behaviour is, I think, predominantly before you're into the nematic phase. It's the surface phase growing, and then the bulk comes in and says, "No, we're doing this, guys."
These correspond to surface stripes rather than surface squares, don't they? In other words, take the bottom one, you've got that all the way in and repeating periodically, so that it does want to go that way to reduce the, so that you have a twist elastic interaction at the sides.
Okay, so we see different behaviour for squares and for stripes, and I'll show you a little bit about rectangles, which tries to join the two together. If I have time, then you have the energy. Where are we? Okay. But I wanted to make this point about the importance of the wetting behaviour in these systems. So I'm going to concentrate now more on what happens at the end, what happens in the final nematic structure, rather than the process by which we get there. So I'll show you what happens if we have a single stripe at the top and uniform homeotropic on the bottom. We get domination by the homeotropic and then the plane of it says, "What about me?" and starts to have an influence. This is the two-stripe system in phase with each other. And this is the behaviour that comes out. This is the high density arrangement here. This looks like a vertical aligned region and a horizontally aligned region by eye. That's not quite correct. There is tilt in this system. The tilt is in the plane of the stripe. The surface region, certainly the green bit there, lines straight along the stripe axis, and the surface ones here pointing vertically up. In fact, in the bulk, the two regions do tilt round a little bit to correspond with each other a bit, and we can look at that more systematically rather than with a single snapshot by looking at these profiles of the order parameter. So this one on the left. So I've got two sets of data here. I've got lines, which are the data for a system which is random planar aligned, top surface and bottom surface, and that's what the lines do. And they show, as we, that's the symbols. That's the symbol data. And the symbols data clearly goes red and green, and then, So red and then green and then blue. So as we increase the density, the order parameter, the alignment with the surface increases as we increase the density. Whereas between the green regions here, we see, which is the lines, we see much less in-plane order in the centre of the film. We see much less surface order in the surface alignment in the centre of the film because this guy is sitting next to this blue region over here. It's got two domains, both of which are tilted, neither of which are aligned with what they would be doing in the absence of the neighbouring stripe. So we see distortions to the profile data here. That blue line is only partially planar compared with what it would be for the fully planar aligned system. Similarly, the perfectly homeotropic system, which is the blue symbols, correspond to this data, and between the red regions here, that gets pulled down. That's because within the simulation, that blue profile is sitting next to that blue profile, in that those blue particles are sitting next to those green particles. This is a pretty rough video showing an entire compression sequence. There are big gaps between each frame in this video. This is how we run these simulations. We start off, we keep the film thickness constant, and we gradually compress it in the X and Y directions. And you can see the order growing in here. The main reason I'm showing you this is to convince you that all the time within this compression that the central region is always pointing in the plane of the stripe. There's no flipping around. There's no that doesn't even consider lining up orthogonal to the stripe at any point, and it's because of this really dominant elastic term. So this can straightforwardly be explained using continuum theory. This is really from an old paper from Tim Atherton, so it actually goes further and considers what would happen if you put an azimuthal anchoring coefficient in. This is before we started thinking about our simulations. But essentially you can solve this as a two-dimensional system because things vary as a function of z, and also as you go across the stripes, you need a 2D solution rather than the 1D ones that Nigel was talking about last week. I mean, you're giving your talk. It was on the video yesterday. But essentially, there are two potential stable states. There's one which we always see in the simulations, always see in the experimental, where the surface particles want to lie down the stripe. Potentially, that's a stable arrangement where they lie across the stripe. You only see that in practice if you put a really strong direct coupling, an azimuthal term in your anchoring coefficient. Although Tim has also very recently shown that if you consider flexoelectricity, then the sufficient flexoelectric coefficient can push you from the natural elastically preferred state into this orthogonal one. So the flexo term integrates out onto the surface, and I'm sure it's related to the Davidson-Mottram behaviour. But essentially, the free energy minimum is sitting at 0. So you want to lie in the plane of the stripe. What the continuum theory and experiments, in fact nothing, predicts is this, though. We get bridging of domains between the substrates. Now people talk about bridging in terms of phase coexistence, liquid gas or something like that. If you want to get a nanoparticle to engage with a pattern substrate, then bridging is potentially an extra mechanism of getting it. If you can have our Casimir force, we can have our Derrick forces, but bridging provides a kind of a frog's tongue kind of route by which the surface can interact with or come up with a tractor beam to attract an incoming nanoparticle. What we're seeing here is not bridging between different phases, though. We're seeing domains. These are both, we've got nematic and nematic here. They're not separate phases. This is a single phase, so potentially this can run over quite a wide temperature range. We're not having acidic coexistence or anything like that. But for these stripe systems, we see clear signs of that means 8 molecular lengths thick, this system here. It's probably melted away there. We should do the experiment where you share one surface with respect to the other. We're definitely seeing it at that thickness. Potentially what you've got here is a molecular clutch that you can have with magnetic fluids, where this is using the liquid crystalline domains to register the top surface with the bottom surface. We only see this with stripes. I think we only see it with stripes because of this relative stability of the twist domain boundary. It's the seed for these domains are these are the line tensions. All we're putting in here is the line tension corresponding to these top and bottom surfaces. That then grows through the system non-trivially, and these are all liquid, so we've got liquid bridging through oriented domains. Yeah, the matic shouldn't transmit it a torque or stress, but it does here. What else can we do? We can vary the tilt angle, straightforward, and I'll go show you everything. But if we vary the relative widths of the planar aligning and the homeotropic aligning parts of our system, then the tilt angle that results in the centre varies with, as a function of that, the relative homeotropic influence and planar influence. So these are this is the angle with respect to the y-axis as we vary the percentage of homeotropic anchoring surface on our substrate. I can get any tilt angle by varying the relative weighting of the homeotropic to planar aligning. Of course you can. It makes absolute sense. When we have a very small amount of one phase or the other, then the two data sets correspond. We don't get the bridging if the stripes are too narrow. So complete range of tilt angles and monotonic behaviour. So tuning in at your tilt angle is straightforward if you're using this approach.
Yeah, but presumably in a large enough system you have buildings, wouldn't you? Somewhere that tilts like that and others where it tilts like that.
Yeah. Also, in a stripe, well, actually, in a stripe-based system, the answer is, you can get, yes. So the matte defect, yeah, you see that in the experiments, yes. But there are ways of getting rid. You have a very small pre-tilt on one of your surfaces, and you won't get that anymore. You've got that. You have that with any hybrid system, and you get rid of like putting a bit of pre-tilt on the top surface. I balk at the idea of trying to measure the anchoring coefficients in these systems. A nice way of measuring anchoring coefficients is to try and to measure the fluctuation spectrum. But if I'm measuring the fluctuation spectrum, the fact I've got this discontinuity here, horrible. So the mechanical route to determining it seems like the only one I could attempt in simulation. I don't know if experimentally, where you do use similar methods, you use a similar expansion and fix the fluctuation spectrum, essentially. What would happen if you had non-uniform surface?
Well, it depends on the appearance.
Mm.
With light scattering, you measure on something like a micron light scale. So if this is 30 microns, then you have a complicated situation.
Yeah, so you have to bring that other dimension into account.
Okay.
So there's an effective anchoring coefficient here. I think it's virtually immeasurable by any of the nice methods, either experimental or the simulation equivalent, because of this this extra dimension you have to take into consideration. Now that's just 1D patterning. But the experimentalists are very happy to create 2D patterning. How do you then represent that in terms of an anchoring effective anchoring coefficient definition, or in terms of what else is going on? When do I start? Yeah, okay. So I can simulate things with square patterns, and I've showed you the experiments that are done with square patterns. But again, the kind of continuum description of these things is really not straightforward, because you do have to either take into account the fact you've got different anchoring coefficients on the different regions, or you try and come up with some overall anchoring coefficient to describe the entire thing. So with the square system, if we compress it a little bit, so said, this is equal amounts of homeotropic aligning and planar aligning systems. We compress it, the homeotropic wins. Until we compress it some more, and then the effect on the planar region starts coming in, and start seeing some pink behaviour here, you start seeing some tilt, only when we get well into the nematic phase. Okay? And it's because the wetting behaviour of the blue alignment dominates. It's only later on you start seeing the true alignment behaviour. So here the planar parts are really restricted system of monolayer at the transition. It's only later on that the bulk starts tilting over. Here we never get any domains going across, none of those stripes going across. We always see a monodomain in the centre, even for very, very thin films. Whenever we have a two-dimensional pattern, no bridging. Why? Why do we never see any bridging? We wave our hands. Imagine there were an orientational domain bridging between the top and bottom surfaces between two square pattern bits. It would look like this. It's had a single bridge. So we're cutting across this bridge. So I've got homeotropic to homeotropic coming up here. I've got plane to planar coming up through this square region. I think that's got to be unstable. That arrangement has to be unstable, because I've got two different types of domain wall in that system. I've got some twist domain walls, which are represented by the blue lines. I've also got some T domain walls, where the red lines are. And it's the wrong terminology. We shoot me if I say surface tension, because it's the wrong length scale. But the domain boundary strength here is very different from the domain boundary strength here. If I've got an entity with two different surface tensions, then one of the boundaries is going to give way. So that thing's bound to fall apart, simply because it's a two-dimensional pattern, and it involves twist-like boundaries and T-shaped boundaries. That's why we never see, even for incredibly thin simulation films, 2 molecules thick, 1 molecule thick, we never see bridging for 2D. Whereas we see it really quite convincingly, and says, oh, fine for these 1D patterns. So stripes, bridging, not for enormously thick films, but bridging definitely exists for these, for the stripe systems. Whereas anything 2D patterned, be it squares, be it rectangles, be it circles, no, never see bridging going across. So the squared substrate system, what's the if we look at the top of one of these systems in a little video, you see in the planar regions, essentially, they're very small, but they want to line up along the edges of the squares that they're residing in. So either sit at 0 degrees or at 90 degrees and flip between them within a simulation. So that's what you saw there. And they can flip independently of each other, so the one down here goes red for a little while and then flips back to being green. And we do a histogram analysis of the orientation of particles in the surface regions, and yeah, it's not quite 50-50, but it's a Monte Carlo simulation, what do you expect? Virtually all the time they're sitting within 5 degrees or so of either the vertical or the horizontal alignment. That's what the simulations see. The experiments, remember, they said plus 45, minus 45 degrees when we rotated the sample with it between the polarizers. The plane of it was sitting at 45 degrees. Why is that? Well, this is where this can be explained away by the continuum theory from Tim Atherton, which came out last year. You do an elastic theory. It's got to be a two-constant elastic theory. There's some clever bits to it, but you can linearize the Euler-Lagrange equation, and he does a transformation which is rather akin to doing an affine transformation, depending on the azimuth angle that comes out. I won't go into it. I can show it to people, and Tim's very happy to interact with people about that. But essentially, this is what comes out. Depends on the anchoring strength, and it depends on the length scale of the squares that you've got. So the period of the pattern. So the fact that my simulations for the squares, well, my simulations are 1,000 times smaller than my experiments. For the stripes, it didn't matter. I've got the same behaviour, but for the squares, it matters vitally. Essentially, in the strong anchoring, small length scale world of the simulations, we are in this regime up here, which corresponds to line up with the edges of the walls. In the weaker anchoring, larger length scale behaviour of the experiments, we're down in this regime. L theta is the anchoring coefficient. So change the length scale, change the relative anchoring strength, and you get different behaviours. So you get diagonal alignment in the experiments, and you get edge alignment in the simulations. So you've got crossover behaviour. And what that crossover behaviour means that somewhere in the middle, you're going to get bistability between diagonal aligned and edge aligned in those squares. So your planar regions are either going to be diagonally aligned or edge aligned, and according to the theory, there's a bistability between those two alignments. And unlike, Nigel will correct me, almost all the theories I've seen about bistability and experiments I've seen about bistability, you don't have to have stabilizing defects for this system. So ZPD is stabilizing defects. I think your square weld system's got stabilizing defects. But you don't need them here. All you're doing is flipping from diagonal to two diagonal choices to two edge choices, and there's the bistability between those two arrangements. It sits somewhere between where the simulations are and where the experiments that John Bramble did are. But absolutely no need for defects if you get that correct balance of the surface anchoring, the bulk elastic constants, and the length scale. And that's what these lines are showing. So any line which is below this axis is giving the diagonal solution. A line which is above this axis is giving the edge aligned system. So there's plenty of predictions of getting crossover between the two. I said I'd say something briefly about rectangles. I'll say something about rectangles. So I'll say stripes. For the stripe systems, other than the bridging, the experiments and the simulations say the same thing, even though they're very different length scales. For the squares, the two systems disagree because they fall on the opposite sides of this divide. So we can straightforwardly via between squares and stripes go to these things called rectangles. So if we take our squares and we distort them a little bit, how soon does that start influencing things? On the simulations side of things, the answer is pretty quickly. If we have a rectangular ratio of 2 to 1 or definitely 3 to 1, then we get a massive preference for lying along the long edge. These are the red bars here is a system I showed you previously, the histogram for the square pattern system. equally likely to be horizontal and vertical along the two edges. If we make one of the edges just twice as long, that's the green bars, and we've almost completely lost alignments along the short edge. And if we push it up to 3:1, the blue bars, or the stripes system, which is the pink bars, then they're virtually sitting on top of each other. So as soon as you've stretched your square system to be twice as long in one dimension as the other, then you're pinning your azimuthal alignment really strongly in this small, highly anchored system. The experiments, sent John off to go and he said, this looks really exciting, go and do some experiments on this. When he did the experiments on these systems, then these were the azimuthal angles that he obtained. His system, his square system, aspect ratio 1, was of course originally sitting along the 45-degree line. And what happened is he changed the shape of his rectangles, which was harder for him to do than it was for the simulators to do, because he had to make all these stamps and systems. Essentially, the azimuthal angle tracked along the long diagonal, and he never saw it flipping along to the long axis, so he went as far as an aspect ratio of 2:1. But essentially, experimental system tracked the diagonal, whereas in the simulations it jumped straight to saying, we're going to be pinned along the long axis of the rectangle. And again, Erickson Leslie comes along and explains this for us. In the small system, Ly is the periodicity. In the small system, we get lining up with the azimuthal director angle sitting at 0, sitting along the long axis, along the edge of the rectangle. Whereas in the experimental length scales, we lose that minimum at 0 degrees, and we start seeing this minimum at non-zero angles. And depends on precisely what the ratio is, and on the value of this L here is, sorry, it shouldn't be, that's not Ly, that should be L phi, it's the anchoring strength. And in between the two, again, we get this type of behaviour. There should be bistability between edge-aligned systems and diagonally aligned systems. So just as we saw bistability being predicted for the squares, that should carry across for the rectangles as well. It was very nice of Tim to do this, because the experiments and the simulations have been sitting there for some time contradicting each other, and it was only when Tim did the Erickson Leslie for the rectangle systems that we started to believe that each other hadn't made a mistake. It's a very short section in John Bramble's thesis about the rectangular systems, because he didn't understand what the results were, but Tim's work's resolved that for us. And this is the summary. This is the critical parameter ratio of elastic constant anchoring coefficient, and D is the film thickness, which is also an important parameter. And we get edge alignment with a strong anchoring and thin cells, and we can use that to control the strength of the anchoring coefficient. Because when I showed those histograms, what the histograms really represent is so the width of these histograms is a measure of the anchoring coefficient, the azimuthal anchoring coefficient. So we can control that with the shape of the rectangles. In the experiments, what you're controlling is the azimuthal anchoring angle and the azimuthal anchoring coefficient, because the anchoring angle was changing to lie along the long diagonal, but you're also changing the coefficient at the same time. So I shall close with a few conclusions. I'll perhaps labour the point, but homeotropic anchoring and planar wetting are fundamentally different from each other, because you get continuous growth in one case and you don't in the other. You get a sharp jump out of the transition for planar, and that affects a lot of these systems experimentally, simulation. Bear it in mind. We get domain bridging if we have stripes of liquid crystals. You can get coupling between stripe pattern surfaces through a pneumatic liquid. If you vary the width of stripes, you can get any tilt angle you like. If you move to square patterns, then depending on your length scale and your other parameters, you either get diagonal alignments or edge alignments. The experimental systems were really pretty solidly within the diagonal alignment regime, but now we understand more about the edge alignment possibilities, then strengthening the anchoring coefficient might be possible to access it, and then we'll get this really quite straightforward route to biostability, because these things are very easy to produce in principle. If we then vie between stripes and rectangles, then in the small system limit we get really strong alignment with the long edge of the rectangle very quickly, whereas in the larger system, the weaker anchoring system, the azimuthal anchoring tracks around to follow the diagonal. But those rectangular systems do give you additional control over anchoring angle in one case and anchoring coefficient in both cases, which is one of the things we were interested in looking at. I've shown you stripes, I've shown you squares, I've shown you rectangles. A really nice one is circles. Because within circles you've probably got one domain which is covering the entire surface, but does that, particularly if it's the planar domain, does it want to go between nearest neighbours or next nearest neighbours? And that's then another possibility of a transition between orienting vertically and horizontally, or orienting plus or minus 45 degrees. And we see that in simulations, and Tim's seeing it in the theory as well. But there's very simple, I think the switching into biostability in these systems is going to be very, very simple, because you don't have these complications relating to the defects. Sorry, I know you've got a session about defects later on. In the year, defects are wonderful and important things, but if we could get double stable switching without the complications associated with defects, I think they're sitting in there. If we can get experimental systems to sit in that orangey bit in the middle, which sits between John's experiments and Condi's simulations. So thank you for your attention. Thank you for Condi for doing simulations, Tim for doing good theory, John for doing lovely experiments. This was originally funded by EPSA, some stuff from Seiko, Epson, someone else as well, Sharp. And Tim's supported by the NSF. I've done a lot of work with Paolo on very related systems and all density functional theory. And he's had a look at a lot of this. My now retired colleague and mentor Chris Kerr, Fred Baum did a lot of the early simulation work, and so we talked to Nigel about bistable systems and squares and patterns. Thank you for your attention.
Thank you very much. A very interesting talk. Some questions?
Yes. One aspect I didn't completely understand is would be how advantageous would it be to have small scale surface patterns? You talk about different shapes, but achieving refinement, could it favor, say, the range of biostability? I
don't, in terms of devices, I don't think there's much to be gained by going down. The reason I've done the simulations on that scale was because that was as big as the simulations could be. And I think you'd probably start hitting other problems if you went down significantly below the micron scale on the patterning. It can be done. It can be done.
Yeah, well, one reason is this would provide a method, perhaps, for getting a good continuum model through homogenization.
Yeah, I guess if you make the experimental length scale smaller, then you're getting closer to this bistable region that we're suggesting. So, yeah, sorry, I take your point.
Your needle seems to have, your needle potential seems to have an effect on the volume, because the molecules can escape. Right? If you have only 4 molecules, it's like 25% more room for them.
Yeah. So you can, the density values I put here are based on the number of particles within the simulation box. Really, the way we should characterize density is by measuring what the density is at the center of the film. That's a more pragmatic way of doing it. But certainly bits of the particle bits of the molecule are escaping from the system. I'm fairly relaxed about that, because in reality that's kind of what real molecules do as well. If they're embedding themselves into a layer which they like, routinely get aliphatic chains embedding within a SAM or something like that. But yeah, really, that was why I said I wasn't really able to characterize what the transition density was for those systems.
Very quick question. Usually, in principle, I mean, to go from planar to homotropic, you could do many ways. One way would be just to go through a sequence of axis state.
Yeah.
And my question is, have you monitored the degree of excited and so on?
So we've looked quite a lot at hybrid line systems and looking for things like eigenvalue exchange as you track the Q tensor from the bottom substrate to the top substrate, which should be there. We generally failed to find by simple kind of uniaxial systems which show eigenvalue exchange. We do see a lot of surface biaxiality in those systems.
You've got eigenvalue exchange in one of your very first pictures where you had homeotropic chunk, then a planar chunk, and a homeotropic chunk. That's essentially the eigenvalue swapping between two.
Yeah, but if it's not uniaxial, sorry, it doesn't have a single symmetry axis, which is what I mean by.
The degree of axiality inside should increase at some stage.
So there's is it Peter Palfrey? Predicted that you can have a uniaxial symmetry system which goes from random planar at the bottom to uniaxial homeotropic at the top without ever breaking that symmetry about the z-axis. So what was the Zoom? I think it was a Zoom paper with Andrea.
Is that not Chuck?
Anyway, somebody. And actually this is the usual way to induce bistability. Just to straight the record.
Sorry.
You said that there are no ways that you knew of to induce bistability without defects.
Well, I do. Yeah, no.
I mean, it's not mine. It's just George Durant's work.
Yes.
I think at the time where there was this rivalry between the ZBD and the French group. I mean, I was not involved in it, so I'm just neutral. But this was a big debate 20 years ago to go and get bistable devices without defects.
Okay.
And that was George Durand's idea, based on order reconstruction.
Yes.
And to go and biaxiality.
Okay. I'm heartened by that. I can't see any reason why there should be defects, but a lot of the ones that are out there call themselves the defect state and continuous state. And
but if you have a system where you've got defects that cause the bistability, if you just relax the anchoring,
they can go subsurface.
Defects go underneath the surface.
Yeah.
That's essentially what you've got here. So instead of having defects moving around, you've got anchoring breaking instead, in a sense.
Yeah.
And that's
that's right.
exactly the democratized
Yes.
Durand.
Yeah.
I think Margarita had a question.
It's a related comment. I think what you have is actually a dependence on the overall scale of the system. Your system is probably very small, very molecular, and so you don't really need the defect.
So the question that Jim and I had initially was...
I have a second, this is a comment, but how can you in your simulation, I mean your simulation box is only a few molecular diameters, 5? Less than 10? Is there any chance of doing bigger ones to see how you can cross over to the other?
So we can run bigger.
There's certainly an overall dependence on the scale of your system, on the size of your squares compared to the molecule.
Yeah.
And there is a regime where you cross over to these.
So we can make the simulation bigger. That's not a fundamental problem. A more fundamental problem is that almost all the simulation models we have got very strong anchoring coefficients. And I think that's another thing which is that's another barrier, which is between where the simulations are and where the experiments are. We need a simulation model which we can run big systems on, which has also got a weak anchoring coefficient. You agree, Mike?
I would have thought, yes. I mean, certainly I thought it was worth putting some effort to
So
create a surface potential which has weaker anchoring than what we've got. But I don't know if that's the key issue here.
So it's not just, so size size matters, but it's not just size. It's these guys as well.
Is there a problem in simulations with anchoring? Different anchoring coefficients? Yeah.
The problem is basically that all kinds of intermolecular potentials are naturally on a molecular scale, and you can't tweak the potentials sensitively enough to give you an anchoring coefficient which is weak as experimentalists understand it.
Why not?
Well, your walls are not molecular. I mean, your walls are just geometrical with some effective potential.
No, so sometimes experimentally weak anchoring is achieved by putting a ligament down.
In some modified surface.
Yeah, and the thing, well, that's going to do to my simulations CPU time.
The whole thing needs to be tweaked very sensitively, because typically you have a parameter or two that you adjust and it suddenly switches over from being, let's say, planar anchoring to homeotropic anchoring or something like that. You never get a magic set of parameters that generate weak anchoring.
So in fact, in this, what is that continuous system I showed you?
There were these papers by Lejeune and Brochard where they actually introduced a kind of decaying anchoring in space, kind of diluted anchoring energies. I wonder whether this could be done.
In principle, you could iterate the development of potential to give you a desired one-body distribution near the surface. Nobody's done that yet, but it's on a sort of to-do list.
So here I'm going from strong anchoring in one direction to strong anchoring in the other direction, varying the only parameter I had, which is the length of my needle in my system. But even when it's crossing over between homeotropic and planar, the anchoring coefficient is still very strong. It's going from strongly homeotropic to strongly planar. It doesn't go through a very low anchoring
questions,
coefficient.
and then I think we'll have to break for lunch. I've forgotten. Tim has one, and there was another one somewhere.
It's more of a comment, really. Partly to do with Ibrahim's question, which is that, of course, when an experimentalist has something that they perceive as weak anchoring, it often is as a result of some kind of averaging over. It won't be necessarily a patterned surface. It could just be some kind of irregular surface, and the net effect is so. When you're talking about anchoring phenomena, sometimes you're talking about molecular phenomena, and sometimes you're talking about mesoscopic, and that's one of the reasons why anchoring as a sort of as an intellectual process has turned out to be so difficult. And that links into Carmen's question about homogenization, and that's right. In order to be able to do this properly, one needs really some kind of formal mathematical kind of process, and I think Stefano did some of this in his thesis. But nevertheless, I think that there's something, there's really scope for looking at this properly in terms of limits. And a final point about Doug's observation about a switch in the anchoring transition, an anchoring transition close to TNI. And I think this was first observed by Rishenko and Clément in the 1970s, I think, a similar kind of change. And I think that this is something to do with the size of cos squared and cos to the fourth terms being related to the size of the surface of the order parameter at the interface, and some interaction between q terms and q squared terms and stuff like that. At least I vaguely remember getting some results of that.
I'm really not claiming that it's not my result. That's the Leeds group's
No,
result. But
it's
it's over 10 years old, and I don't think it's well recognised.
I'm mentioning that similar phenomenon. I'm just saying that similar phenomena had been observed elsewhere. That's all.
I remember a comment you made in a meeting in Sheffield many moons ago about, well, you go talk about the difficulty of the molecular description and the continuum description, particularly in terms of the anchoring coefficient.
Just one more, then.
Just a very short comment on what Tim was saying. We have experiments which show that the anchoring energy scale the same way as elastic constant. So this really supports this image, this picture that you have a relatively poorly orienting surface, which then elastically goes into the bulk, and sort of this gives you the effective anchoring condition. We have experiments showing.
Doug will be around for most of the rest of the day, actually, so if anybody would like to particularly pursue some of these questions with him, there's a chance to do that, either during lunch or after lunch. He'll be here till at least, I should think, 5 o'clock. Meantime, let's thank him once again.